Hello guys, here in this video we are going to talk about waves. Waves is contained in case 3. Okay, you'll be introduced to it in your case 3, and for GCSE you will dive more deep into it. But here's just an introduction into the world of waves and how things operate, because that's the starting point. Okay, what we know, okay, if you drop a stone, okay, into water, just drop it into a standing water, it's still water. That pattern you notice that flows, that's what we refer to as waves. Okay, in that case, that's what waves. You have other kind of waves too. So what are waves? Waves transmit information or energy from one point to another in the form of signals, but no material object makes that journey. So it looks as if the water is moving in a circle, okay, but actually it's just what you're seeing is the flow of energy, not matter itself, not what particles itself. Okay, so let's say for example you make a call to your friend in another city. Hello, how are you, and all the stuffs. Okay, happens via the audio transmission. Okay, the mic of your phone picks up your voice in form of sound waves. That's the other kind of waves, mechanical as the case may be. So the phone converts your voice into an electrical signal, which then propagates either through copper wires or through antenna in wireless communication. So that's sound wave for you. And for the sea wave or the tide, you have here is an example of mechanical wave. An example of mechanical wave. Now, what are mechanical waves to start with? Basically, they are group of waves or the type of wave that requires a material medium. Okay, there's some waves that don't require material medium. That's the electromagnetic wave. One fascinating thing about mechanical waves is the way that they're measured, and that is given by displacement. So we have mechanical waves, that's a displacement divided by the wavelength. Okay, now since displacement and wavelength, you can have them in let's say centimeters or meters in some other cases. Either way, you have both units cancelling out each other, so it's this ratio is unitless. All right, now when this dimensionless factor is 1, it's a ratio. Okay, it generates harmonic effects, which results in doublets. Once the factor exceeds 1, that means the displacement has to be much more than the way you have your wavelength. You should know what the wavelength is. Basically, it's the distance covered by a full cycle of the wave, usually measured from peak to peak or trough to trough. What you have here, that's the peak. This point where you have a bulge in the wave, the highest point here, that's what we call the peak. Then the point of lowest displacement, more like a dip. This point right here, that's the trough. If you have a wave, the measurement of a peak point to the other, that's one wavelength. Okay, that's one wavelength. Okay, then in some cases when you do a measurement of from trough to crest, okay, so here that's your half wave length, and we can continue dividing that way. Okay, that's that for wavelength. Then for the crest, or what we call the peak, I mentioned that earlier, is the highest point above the rest position. Okay, then the trough is the lowest point, that's the point of lowest displacement. Okay, now for the amplitude, okay, fine, we can have a number of troughs. Okay, you can have a trough as high as this, you can have something like this, then you have something like this. So let's say this is your equilibrium position. Now of these three, your amplitude will be this guy. Okay, now for these ones, yeah, there's a displacement, but it's not the maximum. So amplitude is concerned about where they have the maximum displacement from the rest position, and it could even be maybe something like this. Here your amplitude will be this. So guys, don't mind my drawing, it's not perfect. Okay, so here that's the trough, but still that's where you have your maximum displacement. Okay, then the equilibrium position is on text. You can find it as the rest position. That's where you have, you know, when it's more like when you have a pendulum that moves back and forth. The middle is usually where the equilibrium position is, so it moves back and forth trying to balance itself here. So that's what happens here. Those are the waves, the flow of energy. Okay, you have the trough and the peak, and this is more like a balance point. All right, so two more terminologies. Okay, here we'll have the frequency. Basically the frequency is the number of waves passing a point each second. If you check this first diagram and this second one, we discover here that you can count more peaks. Okay, let's say here you have, you can count 1, 2, 3, 4. Okay, let's count the cycle of this. The reason why we have this, that's your lambda. This sign is called the lambda. Here, if you should check of this, how many cycles do we have? This is half. So here we have 1, 2, 3, 4. Okay, 1, 2, 3, 4, 4 cycles. How many do we have here? Just 2.5. So here the peaks of a higher frequency, and here you have a low frequency, and then you have the period. Okay, the period is the time taken for the full cycle of the wave, usually measured from peak to peak or trough to trough. I think I showed you guys that earlier, from peak to peak, or it could be from trough to trough if you want to measure the cycle. Just piece that to get the frequency you have that, and it's measured in hertz. Okay, you have, oh sorry guys, this is a mistake, this should be hertz, then this should be seconds. Okay, I actually did a swap there, which I just noticed now. All right. Okay, then we'll have the velocity. Velocity talks about how fast the speed of a wave, how fast is the energy flowing. Now velocity is measured in meters per second. You should have that from your study of motion. Now the velocity in this case is f, that's the frequency, multiplied by the wavelength, that's f lambda. Okay, so in this case the relationship between frequency and velocity, remember that that's your f lambda. Okay, as the frequency increases, your velocity too would increase, because there's a direct relationship between them. Okay, let's look at the relationship between wavelength and velocity. It's indirect. Yeah, as the wavelength too is increasing, the velocity too what increases. What else do we have now? Period and frequency. The equation that connects period and frequency is frequency equals 1 over period. Okay, it's an inverse relationship, and as frequency increases, okay, this guy decreases, and the other way around if you should swap them. Okay, so as then if you swap these guys, if you make period the subjects, okay, it becomes this. Same thing happens. Increase the period, the frequency decreases. Smaller period, higher frequency. smaller period, higher frequency, and the frequency. Once the frequency increases, the velocity also increases. Remember, direct relationship. Well, for longitudinal waves, you can see from the diagram here that the direction of the wave is on the same direction with the energy transfer. So whatever direction they're headed towards has to be the same. And for transverse wave, it's actually the other way around. The direction of the wave is perpendicular to that of the energy transfer, as you can see here. And these are typical examples for you. This is how you have your sound waves. So that's it, guys. If you have questions, please put them in the comment section, and we'll attend to them.